Okay, today's answers for the mock test we did yesterday are posted. The test was made from your textbook. I used, for the first question, chapter 17, number 13. And the question asks, if you make up a buffer with the concentrations we've listed here, which are 50 mLs of 0.15 molar acetic acid and 50 mLs of 0.2 molar sodium acetate, what will be the pH? And I ask you to do it in two different ways. In the first way, you use an ice table. And the first snag you might hit when solving this problem is that you put the wrong concentrations in the ice table. When you add 50 mLs to 50 mLs, you have a total volume now of 100 mLs, which is going to have all your concentrations. So your 0.15 molar acetic acid is now going to be down to 0.075. Your 0.2 molar acetate anion concentration is going to be down to 0.1. So those are the values that you have to enter into your ice table. And what we do is we also attribute a variable x. X represents the amount of acetic acid that's going to dissociate from the 0.075, which is going to generate X amount of acetate anion, and it's also going to generate X of the H plus concentration. So at equilibrium, we're going to have 0.075 minus X of the acetic acid, 0.1 plus X, because we already had 0.1 molar of the acetate anion, and it's going to generate X of the H plus. Here is the equilibrium concentration. This is the Ka of acetic acid. Products over reactants. We set up a trinomial by cross-multiplying. And we plug in the values into a calculator that has a quadratic function. That's the one. If you don't have it, then you've got to use the quadratic formula. And you get two values. You discard the negative value because you can't have a negative concentration unless you set up your variables incorrectly. Then the math will make up for your efficiency. But if you set up your value correctly, then a negative concentration should be discarded. And so this is the correct answer for the H plus concentration, as well as the amount of acetate anion that further dissolved and how much acetate anion appears. Sorry, acetic acid and acetate ion. Plug that into the pH equation and you get a pH of 4.87. You can also solve the same equation using the Henderson-Hasselbalch equation. All you have to do is find out what the pKa of acetic acid is by taking the negative log of the Ka. That gives you 4.74. The concentrations of the acetate anion, recall, are 0.1, not 0.2, because you've added these two quantities together to make a total volume of 100. And the acetic acid concentration is 0.075. When you plug the numbers into the Henderson-Hasselbalch equation, you get 4.86. There's a slight discrepancy. I really don't know where it comes from. Chemically speaking, it's not really significant. It just bothers me a little bit mathematically. I think it's because the calculator might do something that introduces a tiny amount of error, but it only appears around the third decimal place. In the second question, there are no further questions on number one. So for number two, we have, the problem comes from number 17 in your textbook. You were asked to mix, let me just see one thing. You're asked, what is the pH of a buffer prepared by adding 5 grams of ammonia and 20 grams of ammonium chloride? So you might be tempted to ask, well, why are you then only using ammonium? Well, because the ammonium chloride dissociates into ammonium ions and chloride anions. Chloride anions of this are just spectators, but when you measure out 20 grams of ammonium chloride, you have to include the mass of the ammonium. That's why I'm throwing in that 35. That's for the molar mass of chlorine. Because when you prepare the solution, the chlorine is incorporated in the solid. And once you throw it in the solution, it dissociates into only ammonium ions. The ammonia will abstract the proton from water, generating ammonium as well, and the hydroxide anion. What I've done here is divided the grams of ammonia by the molar mass of ammonia to find out how many moles of ammonia. This is the molar mass of ammonia here, and this is the number of moles of ammonia. The total volume of the solution is 2.5, and here is the molarity of ammonia in my solution. Same steps here for ammonium, except it was 20 grams, so there's the molar concentration of ammonium. Now we can use the Henderson-Hasselbalch equation, but we have to find the Ka value because the Henderson-Hasselbalch equation is set up with pKa. So we are only given the Kb value of ammonia, which is 1.8 times 10 to the minus 5. So to find Ka, we divide it by the autoionization constant for water, Kw. So Kw divided Kb is equal to Ka. And the autoionization constant is 1.0 times 10 to the minus 14. We get 5.5 recurring times 10 to the minus 10 for the value of Ka. From the value of Ka, we can find the pKa of ammonia, which is 9.26. We then plug in all the numbers into the Henderson-Hasselbalch equation, but just pay attention to the fact that A minus over HA signifies that A minus represents the conjugate base. So we have to put the base in the numerator, and the base in this case is ammonia. And the conjugate acid is, or the acid in this case, is ammonium. So when we enter those two concentrations, we find that the pH turns out to be 9.2. Any questions on that one?
Can you explain 1.0 times 10 to the 14 again? And why did you divide by Kb?
Okay, the 1.0 times 10 to the minus 14 is the autoionization constant for water at 25 degrees Celsius. This number comes from the fact that water undergoes autoionization. Two water molecules collide. You can imagine that one of them will pull a proton off of the other one. You'll get a hydronium ion and a hydroxide ion. And if you write the equilibrium for that equation, you get that products over reactants, the concentration of the hydroxide and the hydronium is equal to 1.0 times 10 to the minus 7 for both of those substances. I should write that out first. H hydronium concentration times the hydroxide ion concentration is 1.0 times 10 to the minus 7 at 25 degrees Celsius in pure water. So that constant comes out, when you multiply those two numbers, you get 1.0 times 10 to the minus 14. So whenever an acid-base reaction takes place in water, this equilibrium can have an effect on the pH, because if you have an especially weak acid, the presence of 1.0 times 10 to the minus 7 molar concentration of hydronium can actually affect the pH more than what the very weak acid affects the pH. It also has a certain leveling effect. The presence of certain acids in water will tend to attenuate their acidity because of the presence of the water molecules, and vice versa for bases. So we use Kw to calculate the value of Ka or Kb in aqueous solution. If we're given the Ka of something, we can find out the Kb of its conjugate base, and vice versa. If we have the Kb of a weak base, we can find the Ka of its conjugate acid by dividing it into the autoionization constant for water. And this is sensitive to temperature. When we write this number, we're assuming the reaction is taking place at 25 degrees Celsius, because when you change the temperature, the constant also changes. All right, the third question is based on titrations. How many milliliters of 0.085 molar sodium hydroxide are required to titrate each of the following solutions to the equivalence point? This is adapted from number 17, chapter 17, question number 37 from our text. I used a little shortcut here. Whenever we reach the equivalence point, we can use the same equation as is used in the dilution. The molarity of a solution times its volume is equal to the number of moles. And because in a titration, at equivalence point, the moles of titrant equals the moles of the substance being titrated, then we can use this equation and put down the answer right off the bat in one line. So here's what's being titrated. Nitric acid, 40 milliliters of 0.09 molar nitric acid is being titrated with 0.085 molar sodium hydroxide. What volume of sodium hydroxide do we need? Turns out to be 42 mLs. You'll notice in this one I actually converted to liters so that the units would equate into moles. But in the next step, I didn't even bother, because milliliters here and milliliters there will cancel anyway. what we're really looking for is an answer in milliliters, and as long as the units cancel, we don't really care what milliliters times molarity equals. It's not a useful unit, but we're not looking for that. We're looking for the milliliters of V2. So I didn't bother to convert to liters here because it was just a useless added-on step. Just be aware of the fact that in a titration, M1V1 equals M2V2 can only be used if you're at equivalence. If you use it any other time, you'll get the wrong answer. And the last question they were asked, 50 mLs of a solution that contains 1.85 grams of hydrochloric acid per liter is titrated. How many mLs of the 0.085 molar sodium hydroxide do you need to titrate it? So what we have to do there is find out what 1.85 grams of hydrochloric acid is equal to in number of moles. Divide by the molar mass of hydrochloric acid, that gives you the moles of hydrochloric acid, and then divide by 1 liter to give you the molarity. And then just plug it into the equation we have here. Turns out you need 29.8 milliliters of hydrochloric acid to titrate the solution. Questions? Okay, good. Last question. Number 4 comes from the number 88 in chapter 17. It says a saturated solution of magnesium hydroxide in water has a pH of 10.38. Estimate the KSP for this compound. First of all, we have to define what the KSP is for this equation. Magnesium hydroxide is a marginally soluble substance. It dissociates into magnesium cations and hydroxide anions. This is the KSP expression for it. The hydroxide ion concentration has to be raised to the power of 2 because it has a stoichiometry of 2 to 1 compared to magnesium. The pH we're told is 10.38, so we can find out the pOH by subtracting it from 14. So we get pOH of 3.62. From the pOH, you can find the OH minus concentration by taking the inverse log of that number, which is equivalent to raising 10 to the power of negative 3.62. You get a hydroxide ion concentration of roughly 2.4 times 10 to the minus 4 molar. We also might interject at this point that the magnesium cation concentration is going to be half the concentration of hydroxide because of this stoichiometry. So taking half of this number gives us this number, and then we just plug them into the KSP equilibrium equation. Here's the magnesium cation concentration, here's the hydroxide ion concentration raised to the power of 2. Multiply those two numbers, you get 6.9 times 10 to the minus 12. I only reported it to two significant figures because reporting KSP values to anything more than 2 significant figures is probably not really realistic because there are other forces that supervene in the dissolution of substances that make it kind of, make it impossible to state, make it unrealistic to state the KSP value to anything more than 2 significant figures unless you're introducing all sorts of other equations to account for other phenomena that take place, like for example ionic strengths which affect the dissolution of substances. Yes?
So can you explain the inverse log and how it's used to find the concentration?
Okay, the inverse log is basically, when you take a logarithm, it's a power. So you're saying, for example, log to the base 10 of 1,000 is equal to 3, which is the way, it's another way of saying, it's just a fancy way of saying 10 to the 3 equals 1,000. So if I'm given this number, I want to find this number, and I'm told that the base is 10. What do I have to raise? And I'm told that the power is 3. 10 to the 3 is going to give me 1,000. So, but this time, if I've said that the base is 10, but the power is negative 3.62, which is what the pOH symbolizes, then I'm just saying what number do I get when I raise 10 to the power of negative 3.62? That's the concentration of hydroxide. So if I said 10 to the minus 3, then I know it's going to be 1 over 1,000. So the concentration, it's the pH scale and the pOH scale are devised for reporting a vast range of concentrations because pHs can vary from anywhere from -1 to 14. So they, in fact, even more than -1, you can get certain concentrated acids that have a pH in the negative range. So it's simply a way of reporting in a very vast range of concentration possibilities. The pH scale, it gives you that versatility. Does that answer your question? Okay, good.